optical multiplexer unit that does the multiplexing. You have the optical demultiplexer unit that does the multiplexing, and we have the optical amplifier that's for amplification. And the optical amplifier can be either a boost amplifier, that is a BA, or line amplifier, or a preamplifier, depending on the positioning of the amplifier. If it's positioned just immediately after the optical multiplexer, we call that a B boost amplifier. If it's within the somewhere in between along the fiber route, we call that optical line amplifier. And if it's positioned just before the demultiplexer, it's a preamplifier. Then the other component is the supervisory channel. This can be either optical supervisory or electrical supervisory. The optical supervisory has a separate lambda or wavelength that is used to carry the optical supervisory bits, while the electrical supervisory, this is attached to the OTU itself. So basically, this inherits from the old SDH setup, where you have the line board carrying also the supervisory. Next, WDM sites can be, or stations can be categorized broadly into three categories. So you have the optical add drop stations, you have the optical line amplifier stations, and regeneration stations. Now, depending on what components, basically these major components, depending on the setup or configuration on each site, the site will be either optical add drop if it has OTU, the multiplexer, the amplifiers, and the supervisory. For the optical line amplifier, you basically have amplifiers and the supervisory. And then for the regenerator stations, the OTUs will be used to regenerate. There is no adding and dropping. Basically, all the lambdas that are coming into the station exit out of the station on the opposite side. So a key to note here is that regeneration cleans the signal, while amplification decreases the OSNR of the signal. Now, the technology that is used on the DWDM is basically called Optical Transport Network, OTN, and it's a multiplexing technology and it inherits concepts from the old SDH technology. So this OTN is comprised of two layers of multiplexing. So there's the electrical layer and the optical layer. Electrical layer, that's where the electrical multiplexing takes place. Optical layer, that's where optical multiplexing takes place. So even in the setup that we currently have, the sub-racks that are installed on each site will basically broadly be categorized into either electrical sub-racks or optical sub-racks. Electrical sub-racks will be carrying the electrical layer boards, then optical sub-racks will be carrying the optical layer boards. So the electrical layer will mainly consist of the cross-connect boards, the tributary boards, and the line boards. And then optical layer, that's where you have the optical multiplexer, optical amplifier, the OSC, and maybe the FIUs and the rest. So in terms of trails, the multiplexing structure is from client to ODUK to OTUK, OCH, then OMS, and then OTS. So from client to OTU to OTU, that's the electrical layer. So basically here we have the frames, the packets. That's where that that's how we categorize the electrical layer trails. And then for the optical layer, you have OSNR, you have receive signal power. That's what basically categorizes the optical layer trails. And then how from end to end the electrical layer trails, basically client trails begin from the OTU, actually from outside the OTU, that is basically from the tributary board all the way to the tributary board on the opposite side. Then you have ODUK and OTUK that begin from inside the OTU board from one side to the OTU board of the other side. Then OCH is basically optical signal begins from just behind the multiplexer on one side and after the multiplexer on the opposite side. Then OMS, that is basically multiplexers, between multiplexer and the multiplexer pair, that creates one OMS group. Then OTS is between amplifiers. So from one optical amplifier to the next optical amplifier, that section is one OTS. Then from one multiplexer to another demultiplexer, that is OMS. Then from OTU to OTU, you have OCH, OTUK, and ODU4. Then from one tributary board to the other tributary board, that's why you have a client. So going to the setup that we currently have, we have a FODEM, which stands for Fixed Optical Add-Drop Multiplexing. Now, in the FODEM systems, the wavelength routing is fixed. Each port has a specific wavelength assigned to it. And this path is fixed through the network. So basically, say if you connect a line board to port on the M40V board, say M39, you can only expect to receive the signal on D39 at the opposite end. You can't have it on cannot receive it on a different port. So that is how the fixed optical add-drop comes in. Now for the RODEM, that is reconfigurable optical add-drop multiplexing. So here, wavelength can be added, dropped, and rerouted as needed, and this significantly increases network flexibility and efficiency. So with the reconfigurable, it means that the ports on the multiplexer, are not can be configured with any wavelength and any number of wavelengths. So there's no fixed port that lambda for instance, lambda 70 can only be passed through from this port. It can pass it through from any port that you so wish to pass through. The fixed for them had some issues. Mainly the issues are concerned with the pass-through lambdas. So for instance, on that has multiple directions. For instance, like in this picture, say if you have lambdas that are coming from direction 1 and are going to direction 3, so for each lambda, you need to connect a pair of patch cords from the optical multiplex and the multiplexer boards in one direction to the multiplex board in the other direction. So with so many lambdas crisscrossing in this mesh, you have so many patch cords to manage, and that will create an issue. Say you'd have not all patch cords are created equal. Some have higher uh, attenuation than others, so you end up having some lambdas may not go through because the patch cords are broken or they are tightly oiled. So this creates an issue where you have uneven power on different lambdas. So when you have a fiber break and yeah, the fiber is restored, but you introduce some fiber losses, then some lambdas will restore while others will remain down. So Rodem solved this issue by having only one pair of patch cords connecting between the different uh, amplifier boards. So in the setup that we did, we swapped the OSN 6800 sub-racks at 8 sites. We swapped them with the OSN 9800, and we used M12, OSN 9800 M12, and we used OH20 boards. Now there are some other sites that had existing OSN 9800 M12. These were reused, but we added did WSS20 boards. So the RODEM that we implemented is direction and colorless. It also has a capability of supporting 400 bit. So for the colorless bit, basically this is what I explained before, that any port on the OH20 or DWSS20 can add and drop any wavelength and any number of wavelengths. So there is no fixed wavelength for any particular port. Each port can carry any wavelength. As for direction, this comes from the fact that once you add wavelength into maybe an OH20 and or DWSS, only expect them to come out from the L in and L out ports, or the in and out ports of the DWSS20. So the sites where we implemented this are basically in Mbarara, Motundwe, Mbuya, Masindi, Tororo, Malaba, Busia, and then Lira was left out for now because we didn't have enough boards to use as spares. So the boards that were to be used for Lira have been left out to be used as spares, just in case you have any faults on these other sites that we have already cut over. Now introducing the boards. We have the DWSS20 board. Now this one, it's a type of wavelength selective switching board. So basically, it does optical cross connection through wavelength selective switching. So you can add any combination of wavelength through any of the ports AM0 to AM20, and you can also drop any combination of wavelength through the optical interfaces DM01 to DM20. So the interfaces on this board, you have the in and the out. Now these in and out, they connect to the amplifier. So basically this board doesn't have an amplifier on it. There doesn't have amplifiers on it. So in the cases where we had M12 having the DAPXF and M48V and D48V. So basically, this board replaced the M48V and D48 pair, that is the marketplace and the marketplace. And then the rest of the connections remained the same. So over to the right, you can see how the signal flows through this board. So this board has two WSS modules, and one for adding and then another for dropping. So you can add any number of wavelength and any wavelength using the AM ports and drop any number of wavelength using the DM ports. Then next we have the OH20 board. The OH20 board basically combines a number of functionalities. It combines the DWSS. It has two optical amplifiers. It also acts as an FIU, and it also has OSC and OPM, that is for spectrum analysis. So over to the right, we have the signal flow for the OH20 board. You have you have the DWSS module, which basically comprises of the two WSS modules that are in the DWSS20, and you have on these you have ports AM1 to AM20. Those are for adding wavelengths. Then DM1 to DM20 for dropping wavelength. And then you have optical amplifiers. One is designated R for the receive, that is the preamplifier, and then one is designated T for transmit, that is the booster amplifier. And then in you have the XFIU module, which uh, multiplexes the OSC and the main signal. And then out of the XFIU, you have interfaces that connect to the ODF. So in between the amplifier and the XFIU, you have variable optical attenuators. Those are can use to adjust the amount of power that is going into the amplifier or coming out of the amplifier. So the OH20 also has two OSC units. Uh, one transmit uses 1491 nanometer, and then the other uses 1511 nanometer. So for the ports on the OH20, you have L in and L out. Those are basically the same ports that you have on the DAPXF. L in and L out, they serve the same function. They connect to the ODF. Then AM1 to AM20, that those are basically similar to the ports on the M48V or M40V that you use for adding wavelengths. Then DM1 to DM20, those are ports that are similar to the demultiplexer. Use this for demultiplexing. And then you have Mon R and Mon T. These are you can connect these to the spectrum analyzer or PM8. So mon R is for monitoring the signal that is received from the preamplifier. Then mon T is for monitoring that signal that is being transmitted out of the boost amplifier. Now you have some internal ports that are not, they are displayed on the NMS, but physically they are not displayed on the board itself. They are internal. You have TA in, that is the input of the transmitting amplifier. TA out is the output of the transmitting amplifier. You have TVI, which is the input of the variable attenuator on the transmitting amplifier. Then TVO is the output of the variable amplifier on the transmitting direction. RVI is the input for the variable attenuator on the receiving amplifier, and RVO is its output. Then you have ports TC and RC. These are similar to what you have on the DAPXF. RC is receives the signal from the transmitting amplifier, and then TC pushes out the signal from the XFIU to the receiving amplifier. Then you have RM2 TM2 and RM1 TM1, and these are also similar to what you have on the DAPXF. These are where you terminate the OSC board. And then RX1 TX1, RX2 TX2, these are the inputs and outputs of the OSC units. Then you have R in one and R out. These are the inputs and outputs of the DWSS unit. So when you look at the signal flow diagram, the ports will be labeled. Say for instance, we have ports 4 to 22. And in here you have 4 to 22 is on the top right hand side, where you have AM2 to AM20. So those are for adding wavelength. Then 24 to 42 for dropping wavelength. These are physical. They are basically on the, if you look at the picture on that top left, the ports with the blue couplers, those are the ports, and also they are also labeled. There is a key that shows how the ports are labeled, and also how what sequence they are arranged. So at the bottom of the board you have DM AM DM AM. So basically for each row, the first port is a DM port, the second is AM port, then the third is DM port, and then the last is AM port. And then depending on the row number, can either be AM DM1, AM1, DM2, AM2, or whichever row. There is a label to show that this is port 1, this is port 2, and this is DM or AM. So if we move on to the basic configuration, under the WDM interface, have the basic attributes, and for the DWSS 20, the basic attributes basically can only label the interfaces. So since that GWSS OH20 can add or drop any wavelength. It is useful if you label the interfaces so you know that this interface, I've connected this line board. Then for the advanced attributes, this is where you adjust the optical attenuation on each particular lambda. So under this column, gridless optical interface attenuation ratio, that's where I adjust the optical attenuation for each lambda. So the lambdas, the number of lambdas that will appear under here that can be adjusted will depend on the cross connections that have been configured on the NE. For the OH20, still under Dwdm interface, the basic attributes, you can label the interfaces, and you can also adjust the optical attenuation of the receive and transmit amplifiers. You can also adjust the gain of these amplifiers from this interface. And then under advanced attributes, this interface is similar to the DWSS20. You can adjust the attenuation of the lambdas that are configured. Now on to the optical cross connections. So here, since the OH20 and DWSS20 can drop any number of lambdas and any lambda to say, we need to do cross connections, and these cross connections are basically configured logically. So you can cross connect a lambda from one direction and come out through a different direction. So in order to do the cross connections, first you have to delimit the edge ports. So these ones you can either manually select them, or once you create logical fibers between ports, then they will automatically be selected. So in order to manually select them, this interface will show you the available edge ports, and out of these available edge ports, you have the ports, and also you have the default edge ports. Now these default edge ports are the ones that will connect to either. So for the case of the OH20, these are the ports that will connect to the ODF, and then in case of the DWSS20, they are the ports that connect to the DAPXF. It's basically the ones that go to the ODF, the line side optical line. So those are the default edge ports. And then the selected edge ports are the ones that you're going to cross connect with the default edge ports. So once you select the ports to be used among the available ports, you push them to the right among the selected edge ports, and then you apply. From there, then you go to the next tab, which is NE level optical cross connection, and you create the cross connections. So now, under the cross connections, the cross connection will be similar to what we normally do under the SDH configurations. Basically, you click the new button, and then a pop-up window will appear, and in that pop-up you can select the source board and source port, and then the sync board and sync port, and then you can select the wavelength, which is basically the time slot. And then when you click apply, the cross connection will be created, and then it will show you the source wavelength number and the sync wavelength number, and then the source port where that wavelength has been dropped, and the sync port where it is coming from. So that will basically be the end of this presentation. So questions are welcome.
Thank you, Samuel,
Mm.
for taking the team through. I expected some questions when you were explaining the OH20 and the DWSS20. I expected
Okay.
questions from the field team, but no one was even asking. Yes, Matthew, go ahead.
Thank you, Dennis. Hello, Sam. And
Hello.
thank you for the presentation. I have one question.
Okay.
It's regarding the supervisory signal.
Mm.
That we have two wavelengths, the supervisory signals, and I believe and I understand that one core
Yeah.
will represent one port for the supervisory, while the other core will represent the other one.
Yes.
My question will be, how would I be able to determine in a quick way? Because if you have a breakage on one core and the other core is working, you will have a coaxial loss on one of the supervisories, but the other supervisory will be working.
Yes.
Is there a way that I can determine now from the amplifier perspective which core is not okay? Like, is it TX or RX if I'm on site A?
Mm.
Is there a way of determining? Because in most cases, we'll get such queries from the field team. I tell them that I have one core down, one core up. Because I'm seeing one supervisory up, the other one down. Then they'll ask me which direction is not receiving. Is there a way of quickly determining that from the
Yes.
supervisory signal here?
So basically, if on the amplifiers, they have a MUT loss alarm. Okay.
Yes.
So if the receive, if the receive amplifier is attached to the faulty core, then you have a MUT loss on the receive amplifier. So that's how you can determine. So from the amplifier perspective, on the transmitting end, you won't have any alarm on the transmitting amplifier, but on the receiver, on the receiving side, you have a MUT loss on the amplifier.
Okay. Thank you so much.
Mm. So basically here, then if I go back to the board, so here, basically, if this OH20 is on say site A, and you have say the the fiber connected to the L in faulty, then this receive amplifier will have a MUT loss on RA in. So when you check on the alarm, you say that alarm source RA in will have MUT loss. However, if it's on if the broken fiber is on the L out, there will be no alarm on this side, but on the opposite end, you'll have an alarm on either the FIU or the amplifier. If it's connecting, say, for instance, between Mbuya and Mutunda, you have OH20 connected directly to OH20 on the opposite end, then the receiving amplifier in the OH20 on the opposite end will be alarming. However, for the cases where, say for instance, Mbuya towards Luwero, the alarm will be on the amplifier on what? At Bombo, that is receiving from Mbuya. So that is it. Any other question?
Thank you, Sam. This is gracious. Now,
Yes.
I have a team, a number of technicians here. I don't know why they're not asking questions, but on the maintenance side, okay,
Mm. Mm.
can you briefly tell us the common alarms, like maybe the common alarms that NOC can escalate to the field technicians, and how they should interpret them or tell that maybe this is the source of that alarm, just on the maintenance side.
On the maintenance
Maybe,
side.
yes. Yeah.
So basically, the alarms that will require physical intervention from the maintenance side will be basically MUT loss. We also have OSC loss and OTU loss. That is, if you have if the fiber has degraded so much, then you could also have OTU loss reported, but this can be rectified either by increasing the gain of the amplifier or reducing the attenuation on the variable amplifiers. But if that doesn't work, then it would require physical intervention. Let's say maybe you change a patch code that has degraded, or maybe the fiber itself has degraded so much that you need to rectify some to reduce on the fiber losses. So mainly it will be peeled off on the OCHs. Then for the fiber itself, it will be MUT loss or OSC loss. And so it's basically those three. As for the other alarms, that will basically be on client boards, say ODUK, that will be configuration issues. So in terms of intervention from the maintenance, it's loss of frame, OTU loss, OSC loss, and MUT loss. Those three.
Thank you.
And depending on which port is generating the alarm, then you can direct the engineer to the specific port where that requires intervention.
Thank you. Hello.
Hello.
Hey, thank you, sir. I have one. I have an inquiry.
Okay.
For these new boards, I'm seeing on the OSC you have a variable attenuation, and we rely so much on the OSC to monitor the fiber between A and B, between the two stations. But
Yes.
now, what we've observed with this variable attenuation, it keeps changing, and it as well changes the values of the OSC. So it is very hard for us to tell why it is changing, Then second, to know whether there is either degradation, because sometimes you find when it is actually too good from the reference, sometimes you find when it is close to the reference, but it has changed when you check. Before maybe it was 20, now it is at 0, 0. So I don't know, maybe you need to explain why it keeps on changing and how best we can now monitor the fiber between the two stations, because we can't, it is very hard to rely on the amplifier, because any fault along with the route can cause the amplifier power to degrade. But now, if also the OSC keeps on changing, it becomes so hard for us to tell. I don't know how best we can monitor now with this variable attenuation in the OSC.
Now, with regards to this, I think what I can say for now is that can mainly focus on the main signal, since it's the one that is carrying the traffic. So if the degrade is, there's no degrade on the main signal, then we can ignore whatever changes are happening in the OSC. However, I haven't yet gotten around to discussing with the GTAC support to give me an explanation on why the attenuation on these variable attenuators on the OSC just changes erratically. But once I get this explanation, I'll forward it to you.
Okay,
But
I did it.
we can just keep the references of the amplifiers themselves.
And you know, some of the amplifiers actually don't have references. So it is also a challenge, because some you put don't have reference. And also if you have the degradation on another hop, like maybe 3 stations away, you will see the same degradation everywhere. So it is hard for the knock to pinpoint the exact station or the exact hop with the problem. So that's why in most cases we want to use the OSC, because for it it's between stations. So that feature is very important for us.
Okay, but say for instance, say in a multiple hop, you have degrade on one section and then it affects all the amplifiers, but I don't think it would affect all the OSCs. So maybe it might take quite a bit of checking through each section to see which OSC have remained constant. But I will talk to that GTAC and give us an explanation on this.
Morning, Sam. Abdul here.
Yes,
Now, for the transmission bit, since now, as Gracious had highlighted earlier, now, whenever we are troubleshooting at times, I think you need to elaborate. Most of these OSCs are operating on BD. They're doing bi-direction on on the supervisory especially. So it becomes tricky for an engineer who is troubleshooting a degrade, because initially on the 800, if you're doing troubleshooting and you disconnect from the FIU, you'll not be having any optical an optical signal coming from the other end. So right now, which is in the case with the 9800 setup, whereby we have traffic coming, we have optical power coming from all directions. Okay, literally both directions. You find the TX core has both a transmit and a receive of the OSC on the same fiber. So it becomes very tricky. It becomes very tricky for someone who is doing a degrade between OSC to OSC. So I don't know if there is any way that you can really, because we are always literally time and again disturbing Matthew, even in the night, to support whenever we're having the degrade between these two sites. So I don't know if we have a solution to that, or we just have to continue shutting down the laser ports for us to test. That is one. Then secondly, we also need to, you also need to highlight or caution us in respective to the wavelengths that are under operation. As you've said, we are using 1490. I think you mentioned something of 1490 and 1551. So with these two wavelengths, our OTDRs can operate. Actually, most of the teams that are operating are running, their OTDRs are running on two wavelengths, which is 1310 and 1550. And then some OTDRs have 1625 and 1650, which is very hazardous to these laser ports. That's why we end up having issues that the port has been burnt or something like that. So you need to elaborate to us further in that regards of those two matters. Otherwise, you'll find your board burnt. And Abdul will have used 1650 because he's testing a live port, because he's seeing there's fiber on it, it is degraded, and I have nothing to do but to use an OTDR with the filtered wavelength. So you can kindly take us through.
Now, for the case of the OTDR, there is a new feature that was implemented recently in the NCE, NetStar O&M. Basically implements Fiber Doctor, though we have only implemented it for the section from Buya to Kayunga to Tororo. It basically makes use of the OTDR function that is in the OSC itself. So basically all these OSCs that are AST2s, AST4s, and also on the OH20, they have in addition to the OSC, they also have OTDR function where you can do a fiber test and tells you basically everything that the OTDR can tell you. So the intention is that this will be rolled out on all the links that have these OH20s. So in this case, the person that is on the ONMS can carry out the test and inform you. As for the other sites that have not yet been changed, in those ones can still continue to use the OTDR the normal way that they've been using them. As for the OSCs shooting out on both cores, I think this one, I'll also contact the JTAG to see if there is an option where we can have maybe automatic laser shutdown if the port is disconnected from the fiber. But for now, we can only continue with shutting down the lasers.
So Sam, for these sites that for the hoops with the OH20, as I said, we have tried to use through the Kayunga to Tororo hoop. I don't know if because I haven't looked at the report it generates, because I don't know how filtered it is, depending on. So we also need to take us through that for the functionality of the people in transmission, so that we can try to compare on the intelligence of that tool.
Okay.
Because we need to verify the intelligence of the tool so that we can ascertain if it can really give us to the something so filtered that we can really work with, especially in terms of degrades. of analyzing the degrades.
Okay. I'll put up, do a PPT for that, and now we shall schedule a presentation for it as well. Any other questions?
There is Chigozi. Chigozi, please go ahead.
Yes, thanks, Sam, for presentation. Now mine goes to the side of, you see, before, with the other DWDM, we usually got some confusions. They claim that there is a loss, but it is between the cards. Now this one, I don't know whether there is a way we can be with a degrade, but it is affected between your connections. I don't know how you can go about that, because usually we used to test, we get our fibers is the same, but there is a change. And sometimes it was between the OAU, SC2 card, FIU in between there. But this one, I don't know where can I, is it possible so that somewhere there is a problem? If I put in that card, the rest is internally done. No any other connections which can be affected. Thank you.
Basically, for this OH20 board, all these other connections between the amplifiers and the FIUs and the DWSs are all internal. So unless you opened up the board and tampered with it, expect that the whatever connections are inside there will remain pristine as they were just from manufacture. So the only connections that could be affected are external to the board, say from the DM ports and AM ports, and then from the MON ports, L out and L in. As for the DWSS, these are also the same thing, only the connections from the in and out, MON in and MON out, and AM and DM can be affected externally. And in this case, the DWSS connects to the amplifiers. So this one will not be much different from the old setup. For the amplifiers are external to the board. While for the OH20, the amplifiers are inside the board itself. So we expect no losses to be generated by the connection between the amplifiers and the XFI and the DWSS module. So any fiber degress will be to connections external to the board.
Sam, you skipped out on the precautionaries. Yes, we are supposed to undertake when we are working with this with the with the OH20 and the DSS board, the DSS board. So you could just give us the precautionaries, the do's and the don'ts, so that we don't fall victim.
The precaution would say that we avoid we just use those two settings, 1310 and 1550 for the OTDR testing. As for handling the patch codes, maybe we use those fiber removal tools for removing any certain patch code. Other than that, I don't see any other precautions that you would undertake on this that wouldn't undertake on all other codes. Yes. Is there any other question?
Hello.
Hello.
Hello, Sam.
Yes, please.
Sam. I wanted to ask the WSS currently in our network. Is it working? Is it active? Like working?
WSS.
Yes, that yes.
Yeah. Well, that's where the optical cross connections are done. So they are all working.
On the actual network, on the rural network, I wanted you to show us how it works, how we expect it to work, like to understand it better, what we are trying to achieve in case of maybe we have a fault on one side and how it will switch through the lambdas to another direction. I don't know that is possible.
Now what you're talking about there for switching through lambda, now that will be optical SON, and we're not doing optical SON. We are doing electrical SON. So basically, the switching of is basically electrical. We're not doing anything optical. We're not doing optical switching. However, what the OH20 introduces, the OH20 and DWSS introduces in the network is basically it eliminates the use of multiple pairs of patch codes between multiplex and demultiplexer when you're passing through lambdas from, say, if you have say for a site like Buya, you have lambdas coming from Bombo Road side, and they are going to Mutunde. And then you also have lambdas coming from Ginger Road, they are going to Mutunde. Also other lambdas coming from Kayonga going to Mutunde. So with each lambda that is coming from one direction going to a different direction, on the old setup for them would require a separate pair of patch codes.
The different patch codes.
Yeah, while for this one, they all pass through the same pair of patch codes. So if there's any degrade, then there's only one pair of patch codes to what? To work with. However, in the old setup, you can have some lambdas are okay, other lambdas are not okay. So things like that. So in this case, all lambdas will either be okay or they will not be okay. And you only have to deal with one pair of patch codes.
Okay, then so basically we are eliminating the multiple patch codes we had between multiple sites. Now having one.
Yes.
Okay. I wanted to notice anything for let's say reconfigurable. Yes. What are we doing on that? Is there anything automatically done in the client trails to reduce traffic?
Now on the reconfigurable, basically what the reconfigurable helps you to do is that in case you need to rearrange some lambdas, say for instance, now in the you can have 200 gig. These OH20s you can do 100 gig, you can do 200 gig, you can also do 400 gig on the OH20s. However, in case you have a 100 gig and you don't want to use up all the ports on the OH20, you can connect an M40V and D40 pair of multiplex and demultiplexer onto one port on the OH20, and then you move maybe all the 100 G lambdas onto this multiplexer demultiplexer. So in this case, you don't need to run around the entire network, moving patch codes from this port to this port, this port to this port. You only just need to sit down on the NMS and do cross connection, and you cross connect the lambdas to wherever port you want to drop the lambdas to.
So basically, in short, before with the old setup, if we wanted to add the lambda, we were supposed to send guys and be patching between the stations.
Patching through. Yes.
So basically, in short, with this Dwdm, with the WSS, you've eliminated that patching.
Yeah.
Then on the
Now,
site,
for instance, you could be having, say for instance, in the case of the northern ring, we only have one lambda that is there. Now, say suppose you wanted to add another lambda onto the northern ring, and then you find that maybe that lambda that you wanted to add is going to pass through some section at say from on the eastern ring side, that lambda is used. Okay. And it is free on maybe one section, but it is used on a different section. So you can decide to free it up on this other section where it is used by shifting whichever lambda that is occupying it to a different lambda without going and doing physical patching on site.
I get that. So, apart from eliminating that workload of manual patching, is there any other advantage of WSS in terms of switching, traffic rerouting?
Yeah, the other advantage is that with this WSS, we shall be able to do 400 gig lambdas at drop, which we couldn't do with M48G and and the M40 and B40. So with increasing capacity and speed, the 100 gig are becoming less and less applicable. And so that's why you see we have been using 200 gig on most of the lambdas that we've been deploying recently.
The other one, on top of the eliminating the manual patches, and also we can have a 400 gig CHL. Is there another advantage? I'm interested in is it making my life easier in case I have a cut at Kayunga and maybe Kayunga and Ginger? Can it automatically route maybe clients through another route? Or I have to intervene manually and make some changes? Hello? Hello? Hello?
This is Peter, and I'm a field technician. So my
Yeah.
question is,
You hold on for Sam to rejoin. I think he has dropped off the call. Let him rejoin. Martin, for your case, to not automatically reroute. Basically, it's about the setup for the fixed optical add and drop. If you had say 5 directions or 6 directions at Mbuya, you had a sub rack with all those different boards, the amplifier, the FIU, and the multiplexer, different boards all in the same sub rack. So, but with the RODEM, now you have one board for each direction. So you reduced on the space, you also reduced on the interconnections in terms of the fibers, and you reduced on the power, and also basically it's about the setup. The protection is the same like what you had before. Let's see if Samuel can rejoin. Let's see.
Mindy. Okay. I've been waiting. Sorry,
Okay,
my
Sam is back. Someone was asking a question. So I think it's Ocheng.
yeah, good afternoon, everyone. I'm called Ocheng Peter. I'm a technician from Hoima.
yes, please.
I needed just some elaboration on the wavelengths, the mostly wavelengths that can cause damage to these transceiver ports, as Abdul asked. This port that is receiving and transmitting. Why I'm asking this, for you to give us most of the dangerous wavelengths, because the common one we use is 1310, 1550, then 162. But why I'm asking is sometimes we get support from members who could not be in this meeting now, such that I advise the person to always set his OTDR on a particular wavelength that may not cause damage to these equipments. So I wanted the wavelengths that can be recommended that cannot cause damage, and the other ones that we may avoid. Thank you.
As I had said earlier on, you should use the 1310 and the 1550. The others might cause damage because the boards are only working in the C band and the L band. So beyond that, it cause issues. Hello. Hello. Any other?
Hello, team.
Okay.
Chigos, you still, I see your hand is raised.
No, it was raised before, but now I'm okay. I asked the question, boss.
Okay, because I see it is still raised. So can I assume that we are done? Okay, I see Romano. Romano, please go ahead.
Yes, I'm sorry.
and I've joined lately. There's something I wanted to ask about DWDM. Why is DWDM like? Why should we use put other links on DWDM? Like, why should we use it? What's the advantage?
The advantage of WDM.
Yeah.
So, the main advantage for WDM is that you can carry your signals over a very long distance, because we use amplifiers along the fiber route. And while for the other technologies that are basically using the gray light, you don't have amplifiers in the system, or maybe if you are to implement amplifiers, then the system will be too expensive for that. So rather, you have a separate WDM network where you can pack all your other signals, and then you can multiplex them and use only one pair of fibers compared to having multiple pairs of fibers. Does that answer your question, or need further elaboration?
Romano, is it okay?
It's okay, but maybe I don't know if there is any PDF which you can share for us. Like, I've totally joined it late. I really apologize for that. I wanted to read something more about it. If there is any reference, you can refer me to.
I'll share the PPT.
Okay, then I see Moses Mutebi. Moses?
Yes, Moses has a question. Hello. My question is there with this new hello.
Hello, I can hear you.
With this new technology, will it change our approach to the troubleshooting we have been going through? Or is there going to be a new standard of troubleshooting that we might need to learn as a new approach in our daily operations?
Basically, the approach will not change. The only difference is that with the OH20 board, some of these connections that were basically external have now become internal, so they cannot be accessed, and therefore they won't be damaged, or don't expect any degrade for these connections. So the connections that I talked about are basically the connection between the amplifiers and the FIU, and also from the amplifiers, the WSS. These connections are within the pod, so those ones you expect no intervention on them. The only connections that will be troubleshooted are the ones external to the pod. As for the DWSS, that one will basically go on with the same approach that was there before. Yes, please.
I don't know whether you have an on-site picture of the connections, and maybe you can show us, especially when guys would see
The what?
a picture. Yes, an on-site picture.
The picture of
It's an OS board, how it is connected, like for the guys to see.
Martin,
you mean the one that like the one I showed in the PPT?
No, like the raw picture of the showing the connection.
oh,
How the node is on site.
How the
Because
note
for
is
the
on
node,
site.
they may not get a chance to go there and physically see.
Martin, you
So,
can arrange
Yes.
Mbuya. Mbuya, the nodes are there. So I hope you have access. You can access Mbuya. Mbuya Omutundwe.
Okay, maybe I'll arrange with the. I know
You can
Matthew
arrange with
has.
Matthew.
Abdul has.
You can arrange with Matthew and go and have a physical look on how the nodes looks on how the boards look like.
Okay. Okay.
Timothy, you have a question?
Hello, good morning. I have one question. I just wanted to find out during maybe the troubleshoot of this DWDM. I've interfaced with some DWDMs having both power on both legs. Let me say RX and TX, and we have power on both legs. Is it the same as this, or we shall be able to test the TX from any side?
there's someone else who addressed this question. The ones that have power on both legs, it's mainly because with the new setup on the OH20, they are using 2 OSC units. So each fiber leg carries the OSC for the forward and reverse for each OSC input. So you have power on each, at least the power for the OSC will be on each leg.
Okay. Any other question, guys?
Have any other question?
Want to close?
Moses.
Hello.
Precious. Hello. Yes. Yes, Moses.
No question from me.
Okay. Martin, I hope it is detailed. The presentation was detailed enough for you for the NOC team. From my side, thank you, Samuel, for taking the team through all the new changes that are happening on the DWDM network. Who is Savio?
Okay.
Yeah, so guys, thanks for everything. Thanks for your time, for making it. And We are always available for any consultations as we walk along the journey of the new adjustment in the new setup. And I'm wishing you a good day.
Good day to you too.
Thank you.